A conical surface, an empty ice cream cone, carries a uniform surface charge of sigma. The height of the cone is h, as is the radius on top of the cone. Find the potential difference between point A, which is the vertex, and B, which is the center of the top of the cone. All right, so start by drawing a picture. So that's going to be the top of the cone. Maybe adequate. We'll see. There's the cone. This is going to be distance h, and this is also going to be h, which means that slope of that triangle is just going to be 1. Because rise over run, rise is h, run's h, slope is 1. Okay, and we're going to put in points A and B real quick. We'll call this point B, we'll call this point A. Yeah, that's fine. A. And maybe big A. Doesn't matter. A and B. And so we're going to start by finding the potential, same as voltage. So I'm going to use the formula that a voltage equals KQ over R. This is just between 2 points. And the idea is we're going to use lots of small points. We're going to integrate them, and using calculus, we will find out the total voltage. So we're going to find the voltage at A. So I'm going to say this gets kind of confusing, but I'm going to go with it. I'm going to say a small bit of V, delta V, is going to be the same as K, a small bit of Q, which is a delta Q, all over R. And it's kind of confusing because voltage is always already a difference. Delta means difference. I mean it for as infinitesimally nearly a small part of voltage. Right, so that seems reasonable. So now we're going to look at for voltage for A, a little arrow here to show this is my train of thought. Let's start by finding delta Q. So delta Q, we're going to find delta Q by looking at sigma. So sigma is the surface charge density. So what we're going to do here is we're going to look at A, and we're going to look at the voltage at A from a section of the cone. I'm going to say that section right there. So then if I take that section, move it over to the side so I can look at it a little bit differently, it's going to look something kind of like, let's say like this. So this is just a slice of the cone, and this is going to be A. And from here then, this I'm going to call Z, because we're going to be going, I'm going to integrate from the bottom. This will be Z equals 0 up until Z equals H. So I'm going to call that Z. And since there's a 1-to-1 ratio between the radius, the cone, and the height, this is also going to be Z. This distance right here is going to be R, the radius, right there. And yes. So sigma, that's the picture for that portion. So for sigma, I'm going to say that sigma is defined as a small bit of charge for a small bit of area. So the small bit of charge, that's just going to be delta Q, it's kind of what we're looking for, so we're going to leave it as such. And then the area is going to be the area of this cone, this slice of a cone. And so what we're going to do is we're going to use the circle here. And so it's going to be, the area of a circle is 2 pi r. 2 pi r. That's going to be the area around this part right there. But now we want the depth of it, because it's just, we need an area. We have dimensional analysis, we're going to need to have distance squared. So this is one distance, 2 pi r. And for the section, so I'm going to uncurl this, so to speak. And it's going to look like this. Sort of, maybe. I'm good with that. We'll see. So 2 pi r is this distance up here. And I'm going to say it's the top, it's similar on the top and bottom. And over here, this height right here is going to be delta z. But it's also going to lean over by delta z over here. And so the point I'm getting at is we can't use delta z for our height. We need to use the hypotenuse here. So it's going to be delta z squared plus delta z squared square rooted. And that's going to be, I'm going to call this RH, and it's the only time I'm going to call it that, just so you're like, oh, okay, R hypotenuse kind of thing going on there. I know, extra confusing, probably unnecessary. Long story short, we're not going to use delta z, we're going to use square root of 2 delta z to account for the fact that this cone is going sideways, and that angle there is just 1 to 1. And this r right here, this r is going to be this radius right there, and so this is going to be the same as 2 pi z. So this is going to be the length of our surface area. This is going to be the height of our surface area. We multiply them together, we get the surface area. So I'm going to do that right here. 2 pi z times square root of 2 delta z. All right. So we have this, put them all together, make something reasonable. We're going to get delta q equals sigma 2, I can do it better, 2 pi z square root of 2 delta z. There we go. Now we need to find r. So r equals the radius here, we can just see straight from this picture, it's going to be the hypotenuse. So z squared plus z squared square rooted. So it's going to be the square root of quantity 2z squared, i.e. r equals square root of 2z. Not too bad, not too bad. All right, we got this. So now we'll put this together to find the voltage at A. Voltage at A, therefore, is K, which is the same as 1 over 4 pi epsilon naught, sigma 2 pi z square root of 2 delta z. And this is actually a delta v because it's a small portion of v, all over, and we're going to divide by r, which is going to be square root of 2 z. Get a different color so I can cancel. Square root of 2's cancel, z's cancel. Integrate from 0 to h to get rid of the delta. These are all constants, there's no z's involved, so the integral of 1 dz, this delta z becomes dz, it's just going to be z. And then z is going to go from h to 0. When z is h, total answer is h. When z is 0, it's 0. Long story short, k sigma 2 pi, I'll make it 2 better so I don't get it too confused with the z, 2 pi times h. And this is going to be the voltage at A. Not too bad, almost reasonable. All right, so now for the slightly more nuanced portion, we're going to do the exact same thing. Voltage at B. So voltage at B is up here. We're going to use the same formula for voltage, and we're going to say that a small bit of voltage equals K, small bit of charge, over radius. So now we're going to say that delta Q, to find delta Q, I'm going to move it down here just to give myself a little bit more space. And I'm going to change to light blue because I've grown fond of the color light blue. I'm going to say that sigma equals a little bit of Q over a little bit of area. A little bit of Q is just going to be a little bit of Q, delta Q, that's what we're trying to find. And the area this time it's going to be very similar, except now, instead of our r being over here, our r is going to be over here. And this makes it a little bit more exciting. So I'm going to draw my cone again. That's probably actually a much better picture. So we're going to look at this section right here. This is going to be the center line. And so this distance, we're going to call this 0. We're going to call this h. We're going to integrate going down. So this distance right here is going to be z. But this radius right here, instead of being z, that is going to be h minus z. So when z is 0, h minus 0 is h, which means that this radius up here is h. Down the bottom, when z is h, we get h minus h, which is 0, which makes sense. The radius of that tip is going to be 0. So that seems plausible. All right, so now let's take a look at how we put this together. The change in area is going to be the same thing. We're going to do 2 pi r, except r this time is going to be 2 pi, and this is going to be h minus z. And the thickness, as before, is going to be the same. It's going to be square root of 2 delta z. Square root of 2, is that each area? Let me take a look at that quick. So let's see here. We look at this, so it's going to look like this. I want the area of this sort of thing. Yes. So that radius, r, is h minus z. And that right there, that length, is going to be square root of 2 delta z. Yep, so it's going to be 2 pi r, which is 2 pi h minus z times square root of 2 delta z. Excellent, excellent. All right, so solving for delta q equals sigma 2 pi h minus z square root of 2 delta z. Yes. Now we need to find r. So because we want to do voltage is k delta q over r. So r is going to be this radius right here. And that radius is going to be z squared plus h minus z quantity squared square rooted. So I can probably just write this up right here. Let's see, let's go over to yellow. I like using bright colors with a dark background. It's something nice about it. I really like how it pops. Z squared plus h minus z squared square rooted. All right, so now putting this all together, a small bit of voltage B equals delta Q, K delta Q. So it's going to be K times sigma 2 pi h minus z square root of 2 delta z all over z squared plus h minus z squared quantity square rooted. So now I'm going to take quite a kind of a radical turn, which involves foreshadowing. So they gave us this identity. This integral is going to be a challenge to solve. So they give us an identity. And specifically, this identity has an x up top. So what we need to do is we need to get our variable, which in the case we're using z, alone by itself. We have h minus z, and we need it just to be z, or just a variable. So this is, if you hadn't seen this sort of trick before, it might be like, oh, that's crazy. How'd you think of it? Well, someone else thought of it, and I just copied them. This is an old way of, you see this a lot with trig substitution, inverse trig things. So I'm going to say u equals h minus z. Therefore, du equals negative dz, which I'm going to simplify one more time as negative du equals dz. And then I'm going to go back up here. I'm going to say that u equals h minus z implies that z equals h minus u. And I'm going to rewrite this equation in terms of u. So now we have k sigma 2 pi square root of 2 times h minus z, which is u. I'm going to put a minus sign over here because dz, delta z, is negative du. We're going to put this all over z squared. So I put z over here. I'm going to change this to z squared, which is h minus u quantity squared, which is the same as h squared minus 2hu. We're doing FOIL. We're foiling the binomial. H squared minus 2hu plus u squared. And then we're going to add, so that's what z squared is going to be. And then h minus z squared is going to be u squared. So writing this all out, going to look like I'm kind of skipping some steps here, and I sort of am. It's going to be h squared minus 2hu plus, and then we're going to have u squared. We're going to pick up another u squared from there, because this is u squared. And so we're going to have 2u squared. I'm going to square root this whole thing. All right, so now we're going to check back up again with our equation. And we're getting closer, except we want to get rid of the, so we have a squared, x squared, and square root. Okay, so we want to get rid of the variable on the u squared. So we'll come back down here. We want to get rid of the variable on the u squared. So to do this, I am going to say h equals square root of 2 times a. Now this is mostly a hunch. I don't have a good way of being like, oh, this is how you recognize this happens. This is more just a feeling that, hey, if I put this in, maybe it'll work. Not reassuring, I know. And it might not work. We'll see. So the way h squared becomes 2a squared. Yep. And so rewriting this, we get equals negative k sigma 2 pi square root of 2 u du over square root of h squared, which is going to be 2a squared, minus 2hu, which is going to be 2 square root of 2. I can write that a little bit nicer. Let's see, 2 square root of 2 times a times u plus 2u squared. All right, so now you can see each of these has a 2 involved. should extend this. And what we're going to do is we're going to factor out the 2. So to factor out the 2 from under the square root, it's going to have to be square rooted. So this is going to become negative k sigma 2 pi square root of 2 all over square root of 2 times the quantity u du over a squared minus, 2. I'll say plus u squared. I know it doesn't help that my a's also look like 2. U squared minus square root of 2 a u. Let's see if that's the form that we want up there. And this whole thing has to be square rooted. So a squared u squared negative square root of 2 au. And I know so far away, so much work. Squared, negative, yep, that looks good. Okay, so it looks like we have it in the correct form now. One other thing we can do is we have a square root of 2 on top and bottom. Those will cancel. So what I'm going to do is I'm now going to take this, put it up here so I can make use of the identity that we're given, and then write this out, because this will be a mess. A little bit of a mess. I know I should be more optimistic, upbeat, but yes, it is. It's a bit tricky and a bit cumbersome. So 2 pi, and now we're going to say that this integral equals that. So we're going to start by doing square root, and I used a for their a, so I'm going to keep that, a squared plus, and I used u, so instead of x, so I'll just do u squared, minus square root of 2 a u, and that closes the square root bracket, plus, they have h here, but I'm going to assume they meant a. Yeah, maybe. I'm going to go with it. It's kind of, it adds an extra level of challenge when you don't even get the right identity to work with. I know, bit frustrating, a bit of a challenge. Not exactly the kind of challenge that I like. A squared plus u squared minus square root of 2 a u plus, and I'll close the square root bracket, plus 2u minus square root of 2a. I know, I left myself a massive amount of space there to work, and it still was barely just enough. All right, so now this is our integral, and we are going to evaluate this from 0 to h. But before we do that, we should probably substitute things back in, because, yes, so we should put back in u and put back in a. So what we're going to do is I'm going to grab all my substitution values that I put up there, bring that down, take a look, see how we're doing. So we're going to start by keeping our constants constant out at the end. And I'm going to start by putting in some of the values. So a squared is, so a squared equals h squared over 2. A equals h over square root of 2. All right, So that's what we're going to need for the h's. So a squared, oh, we had to bring it over a little bit more. I know, it's just so cumbersome. It'd be nice if I should just put this all into a program and be like, substitute back in. Give me an answer. So we have h squared over 2, so the first a squared, plus u squared. And I decided that u squared is, can I leave those as u squared? Should I leave those as u squared? I'm not sure. I think I will for now. I'll substitute just one in. Hopefully it'll clean up, and then we'll see what we're left with. Yeah. U squared minus square root of 2a, which is h over square root of 2 u. This is going to be all square rooted. Plus a, which is h over square root of 2. But we have another square root of 2, so that works out well. Natural log of 2 times the square root of a squared, which is h squared over 2, plus u squared minus square root of 2, h over square root of 2, u, close, plus 2u, 2u, minus square root of 2, h over square root of 2. All right, so I'm going to start by doing some canceling. So the square root of 2's cancel. Those square root of 2's cancel. Those square root of 2's become 2. And those square root of 2's cancel. Yep, and I think I'm going to have to rewrite it again with h minus z, because we're integrating everything with z. So I'm going to say that u equals, yeah, we'll put this in here. So I'm going to put this down here as a reminder. And I'm just going to leave it in terms of h minus z squared, because since we're doing it from 0 to h, a lot of those are going to cancel. So I think it'll actually be simpler to leave it that way. All right, so second round of simplification. I know, so much simplifying, so much algebra. Had to have made a mistake by now. Might have, part of the game. And there's probably algebraically simpler ways of doing this, I just don't. I try and keep things as simple as possible. That way I minimize mistakes, aim small, miss small. Good movie, kind of a tearjerker. H times h minus z, boom, plus h over 2 natural log of 2 square root of h squared over 2 plus h minus z squared minus h times h minus z. And I'm going to have to move some of this out of the way. Close that, plus 2 times h minus z, which I'm just going to write as 2h minus 2z. 2h minus 2z minus h. So I'm going to take the 2h and negative h and just going to write that as a single h. So, I know, terrible boardsmanship. There we go. And that's all part of the natural log. And then this is going to be evaluated from 0 to h. I know it's going to get confusing with the various h's. I should have been more clear with my variables. Okay. Yeah, I think that's pretty well done. So now we're going to evaluate for h first. So we're going to have, of course, our negative k sigma 2 pi. And we're going to have square root of h squared over 2 plus h minus h squared is going to be 0 minus h times 0, because h minus h, but going to be also 0, so that's going to be good, plus h over 2 natural log of 2 square root symbol h squared over 2. The h minus z is going to be 0 because we're plugging in h for z right now. And we're also going to get 0 there, so that's going to be close bracket plus h minus 2h, which becomes negative h. Whoop. So I'm just going to change this plus to a minus h right there. All right, so now we're going to do the same thing, but we're going to plug in, and I'm going to simplify this over here. We don't need these zeros. Well, we do need the zeros, but we just need to know that they exist and leave them unwritten, unstated. So now we're going to do, this is z equals h. This is going to be z equals, that's supposed to be a z, equals 0. Plug this in, copy and paste our constants again. I know, I'm getting a lot of use out of that copy and paste function. So now, change colors just to show that I have moved on with life. Ooh, bright yellow. I don't know, is that too bright? I don't know. Looking at the top equation up here, we get the square root of, we're going to have h squared over 2. We're going to have plus h squared, because h minus 0, minus h squared, because when we plug in 0, we get negative h times h, okay, plus h over 2 natural log of 2 times the square root of h squared over 2 plus h minus z, which is going to be h squared, because we said that h equals, or z equals 0, minus, again, h squared, because now it's negative h times h, close bracket, and this time we're going to do plus h. There we go. Some nuance that happens here. Get a good color for canceling. These h's cancel, the h squared negative h cancels. I'm going to rewrite this once just for clarity. And this gives us the square root of h squared over 2, which is going to be h over square root of 2. Yes. Plus h over 2, natural log of 2, and it's going to be h over 2. Let's see, I need to, does that 2 cover both of those or just one of them? Let me check on the formula real quick, our identity. So that 2 covers just the first portion, just the square root. So let's see here. So that part is correct. Okay, so it'll be 2 times square root of h squared, which would be h over square root of 2. And that's going to, so h squared over square root of 2 times 2, that's just going to be simplified to square root of 2 times h. Because 2 is just square root of 2 times square root of 2. So when you divide by square root of 2, we just get square root of 2. I know, really sounded confusing. I could have explained that better. I did not. Plus h. And I'm going to rewrite this as copy paste h over square root of 2, or h times 1 over square root of 2 plus 1/2. No, I'll leave that. H over square root of 2 plus h over 2 natural log of h times square root of 2 plus 1. Yes. So now I'm going to do something very similar for when h equaled, or z equaled h. And for that, that's going to give us, do some of this quickly because it's all exact same process. That's going to give us, let's see here, h over square root of 2 plus h over 2, and then we're going to have natural log, and we're going to do the same thing. We're going to pull out an h. It's going to be h times square root of 2 minus 1. See, those look similar. Yep, and the only difference should be there's a plus 1 or a minus 1. So this is going to be for z equals h. This is for z equals 0. Now we're going to find both the difference between them. So voltage B is going to equal, we're going to have this on the outside, and then we're going to subtract one of these from the other one. So we're going to do, I'll do this. Whoop. Nope. Make small again. Minus this right here. I know this problem is a bit challenging to follow, and I wish there was an easier way, but sometimes there is not. So what's going to happen here is we have an h minus h over square root of 2 here, h over square root of 2 there, 1 plus, 1's minus. And then we can factor out an h and a 2. So these 2's are going to cancel. We're going to pull out an h. So we're going to have negative k sigma pi h. And since we're subtracting two natural logs, this is going to be natural log of, and we'll divide one by the other, h square root of 2 minus 1 divided by h square root of 2 plus 1. And the h's cancel. I'm going to do a quick sidebar over here. So we have square root of 2 minus 1 over square root of 2 plus 1. To get rid of this, we can do square root of 2 minus 1, square root of 2 minus 1. I think it's called multiplying by the conjugate. And what's going to happen here then, and we can multiply by this because it's just same as multiplying by 1. Square root of 2 minus 1 over square root of 2 minus 1, that's just 1 because the top, bottom, numerator, and denominator are the same. So the bottom is going to be square root of 2 times square root of 2, which is 2 minus 1. And then we're going to have square root of 2 minus square root of 2, which cancels out. Similar to a difference of squares. So square root of 2 times square root of 2 is 2. Square root of 2 times negative 1. So it'll be negative 2 times the square root of 2. Because negative 1 times square root of 2, we'll do that twice. And then we'll do plus 1 because negative 1 times negative 1. The denominator, 2 minus 1, is 1, so I'm not going to worry about it. 2 plus 1 is 3, so 3 minus 2 square root of 2. Let's see, does that feel right? Maybe. So then we get voltage of B equals negative K sigma pi H natural log of 3 minus square root of 2 over 3 minus 2 times square root of 2. Maybe. Seems plausible. So now this gives us the voltage at B. And there's different ways that you can resolve this. This is just the way that I chose. Different ways of looking at it. So now we have voltage at B. We have one thing to notice is this is actually a positive number because this negative and this natural log of a fraction are both going to be negative, so it's going to actually be positive. So to go back to get everything together, voltage A, B, be voltage B minus voltage A, depending on how you want to write it. And so we are going to have this value right there. Whoop, get rid of the box. Minus the voltage of A, which is way up here. Right there. I know, so much smaller and more straightforward than voltage at B. Bring that back down, put it over here, we'll subtract it off, and we'll simplify it slightly. So we're going to do K sigma pi H. So K sigma pi H, K sigma pi and H, times a quantity, natural log of 3 minus 2 square root of 2, minus, and then the only term we have in there is 2. So voltage AB is going to give us that value right there. And that should be the final answer for what we got. So let's recap real quick what we did because there was a lot of craziness that went into this. So we were trying to find, given a conical surface, the potential difference, conical surface with a uniform constant surface charge density, sigma, and we wanted to find out the voltage difference, the electric potential difference between the tip of the cone and in the center of the base. So the tip that we use the same idea here. Voltage equals KQ over R. Then we then said a small bit of voltage will be the same as K small bit of Q, small charge, divided by the radius. We then use sigma to find delta Q, and R is just the distance from one to the other. We then took that little small discrete piece, integrated it in an integral, and then solved. So VA was pretty straightforward. Voltage B took a lot more nuance and massaging so that we could use an identity that's given to us. So a few tricks, a few substitutions, but overall the concepts are fairly straightforward, even if the math itself is a little bit intimidating. So, hope that helped. See you on the next problem.